So to get started here, this is my own personal redemption story. It's about the mistakes I made when transitioning our environment to a test-driven infrastructure and what we have done so far to resolve them. But before I dive into that, what exactly does my team at IBM do? We're known for sports. We do the Australian Open, we do Roland Garros, or the French Open, which is going on right now, Wimbledon, the US Open. We also do a large golf tournament in Georgia. But it's not just sports. We also do IBM.com and all of the digital properties that comprise the IBM.com portfolio. And we have this focus on what we call continuous availability. In fact, we've been running IBM.com with 0 outages and 0 downtime since June of 2001. And in that time span, we actually moved data centers 18 times with 0 seconds of downtime. And we do this across a hybrid cloud. We have 3 private data centers and 4 public cloud regions in the IBM cloud that we serve these digital properties off of. And we do it with a large team. We have 80 plus people in 8 different time zones in 35 work locations. And so we need these tools and methods to let us work independently, yet collaborate when necessary. And our workload is highly mission critical. Our partners and teams spend 50 weeks a year preparing for 2 or less weeks. There's no, oh, we'll fix this next week. That just doesn't happen. They're going to hold the US Open whether we're ready or not, and we have to be ready. And not only is these properties in this time span on the world stage, it's also when they derive most of their revenue. So we have to deliver flawlessly. Now, here was the mistake I made. When I was doing this transformation, I went out there and I surveyed the landscape. And I looked at all the best practices. I said, okay, we're going to move this stuff into Git. We're going to do code reviews. We're going to have a delivery pipeline. We're going to do infrastructure as code. We're going to do local testing. And I made all these changes at once and did not go over very well. It was a lot of change to push through all at once. And the biggest problem we had was that simple tasks that used to take 3 minutes were now taking hours. It used to be I'd log into this server and I'd edit the file and I'd move on to the next thing. And now doing a Git clone, editing the file, committing it, it's going to a code review, building it locally, and it's taking hours. So a 3-minute change was now taking an hour to do. And it was this combination of these best practices, which are great practices, and other challenges within our organization and our structure that was causing these changes to take a long time. The other problems that we faced was that we have to put out a lot of enterprise software. It's part of our platform. And some of the software is very big. We have software that's over 1 gigabyte in size. And if you're working locally and you're trying to do a Vagrant up or a test kitchen and test that, and you're pulling down a 1 gigabyte package every time, that can take a while. And our team is distributed. We have people all over the world. We have a large part of our team is in China. We have people in India. We have people all over the United States, in Europe. And they're not all sitting right next to the source of those binary artifacts. So download time is very important. And they're in remote locations. Either they live in a remote location, possibly, or we send them to one. If we send them to the US Open, there's a fixed amount of bandwidth available for you to download things constantly and test them. And the biggest feedback I got was that this combination of factors was resulting in changes that used to take minutes, taking hours. And I brought this problem onto the team, so I decided this was my problem to work really hard to resolve. So we had to find a solution. And our solution was we moved all of our testing away from local laptops to the cloud. In particular, we're on the IBM cloud. And we use a service that used to be called Blue Box. It's now IBM Private Cloud as a Service. But it's an OpenStack-based cloud. And to do this, we used the Kitchen OpenStack plugin to let us spin up test machines on the cloud and test our changes out there instead of locally. Now, we're still developing locally. We're still doing the Git pulls and the code reviews. But the actual execution of all of our testing takes place now in the IBM cloud. And we're able to do this and make this transition easy because how we manage everyone's laptops. When you come to our team and you start to work on Chef, you run a curl bash. And from that point on, we take over the management of the development tooling on your laptop. So we install Git at the right level. We install Vagrant, VirtualBox, ChefDK, all the things that you need to be able to get your environment going and at the right level. And this is great because it lets us make changes easily and transition things like local testing to cloud testing without a lot of impact or breakage. And so we introduced something we call KCloud. This was our effort to let you have your local testing and also bring in this cloud testing. And what it really was a gem that we wrote called KCloudConvert. And it did a couple of things for us. First thing it does is it reads in your kitchen YAML. And I should back up a little bit. That KCloudConvert, we have access to everyone's bash RC, and so we add it to their environment. So instead of typing kitchen to do a test, it's just KCloud instead. And then under the covers, we read in the kitchen YAML. We validate that they're only testing Red Hat Enterprise Linux, and that's an implementation detail we have that we're moving all our stuff to that platform. So if you're on a different platform, you still test locally, but in our platform for our stuff, it's all Red Hat, so we just validate that. We check the includes, excludes that you might have, because you could be only testing against a version of Red Hat 6 or Red Hat 7, and we want to keep that across the cloud and the local testing. We delete the platform stanza, which is in the kitchen YAML, which doesn't apply when you move it to the OpenStack testing. We then restore those includes, excludes, so you still have them as you test in the cloud. And then we convert the hostname directive. So if you're doing Vagrant, it's like a VM hostname, and if you're on OpenStack, it's server name. So we just transparently move that along for you. And then this was when we found as a learning lesson, we prepend all of your suite names with cloud. And the reason we did this was if you were testing both locally and in the cloud, at the same time you wanted to make sure it worked locally, then check it in the cloud. You get these name conflicts because the way Test Kitchen worked is the suite name identified the resource. And so you would go to test it locally and then do KCloud and would think the service was not running. And so we solved that by prepending all of our suite names with cloud. And then because we did that, we had to set the verifier name directly. If you're familiar with Test Kitchen, it infers the verifier name based on the suite name. Now that we've changed the suite name, we have to explicitly tell it what the verifier name is. And then we write that .kitchen.kcloud.yaml to disk. So this all happens in a matter of milliseconds. And it immediately prepares you to take what you were testing locally and instead now test it in our IBM Cloud test setup. And I kind of thought that was going to be the end of it. Like, okay, I've done this work. I got this gem. I converted it. You're no longer testing locally. Things are going to be really, really quick. And they weren't. And it was very disappointing because I thought I had found, my golden ticket to winning everybody back. We were spending like 7.5 minutes of all tests not actually converging anything. We had 7.5 minutes of time spent in the image boot, image create, the preparing for the test, before we even got to the converge. And 7.5 minutes is a long time to wait for nothing to happen. So we had to attack this. And we attacked it in 4 steps. We attacked the create, the prepare, the converge, and the verify. And those are the 4 test kitchen steps that are out there. So our baseline for create, 1.5 minutes, which if you are typing something, you wait 1.5 minutes, it feels like an eternity if nothing is happening. And I spent a lot of time trying to optimize this, and I realized after the fact I over-optimized it in terms of the amount of time that I saved. But to me, this was the most important step because it's the first one. They all depend upon it. And if things don't immediately start coming back to your laptop as you're testing, the user perception is that it's very slow. So if you can optimize this phase, even if it doesn't impact the overall test time all that much, the user perception is much better and user experience is much better. And that's what I was trying to win back, was that user experience. So I broke my create optimization into 2 different steps, the launch and the boot. The launch was everything up until the first systemd message. Once systemd wrote a log entry, then booting had started. And the initial launch was 22 seconds, which wasn't bad, but it wasn't great. So dug into that a little bit. The first thing I did, I was like, okay, we got this image. It's like 800 megabytes. I will shrink it down. So there were some old kernels in there. I added to my Packer setup to remove those kernels. I then wrote a bunch of zeros to where files were deleted, and that helps compression. And then ran virt sysprep. And for those not familiar with virt sysprep, it prepares a VM by clearing things out and making it ready to be relaunched again. And I was like, perfect. I've cut out like 20% of my file size. My launch time is going to go down by 20%. I'm going to go home early today. It's going to be great. And my image launch time was the exact same. So what I learned is that the image size doesn't really matter that much. These images are cached locally on the hypervisor. On OpenStack systems, it uses copy on write. So it's not even really copying the image that much. It's just creating a clone of it when you change anything. So I learned, okay, don't spend any time on the image optimization. Where else can we get some wins here? I did notice this, though. The round-trip time to look up the UUIDs for the various OpenStack entities was taking 6 seconds. So if you look, there's like an image reference and a network reference and a flavor reference. Each one of those, you have the test kitchen driver calling into OpenStack saying, okay, resolve for me what this name means, and it comes back with a UUID. And then once it gets that, it does it for the flavor and then for the network. And these systems are remote, and so you have this speed of light problem. Each one of these requests was taking about 2 seconds, happening in serial. So we had 6 seconds before we actually told OpenStack, okay, give me a node. So what we did was we submitted a PR. It was merged as pull request 159, and it lets you hard code the UUIDs. And this took 6 seconds off of our image create time. And this was important because that blocks every other optimization. If you don't actually tell your OpenStack system, I need a server, nothing else is going to happen. So it was important to get that part down as quick as possible. And the next thing was Grub. So, Grub timeouts are there. Everyone's familiar with Grub, where it's the thing that comes up when you boot, and you can press escape to get out of it and choose your kernel. And that's great on a laptop or a desktop. On a cloud system, not a lot of benefit. So it just sat there for 5 seconds waiting for input that was never going to happen, which is another 5 seconds before we could do something useful for our users. So drop that to 0, now skips right past that, and we bypass the timeout. So those 2 minor changes, they dropped our launch time in half down to 11 seconds, which is when the actual work could then get started. And then image boot. So out of the gate, and this is a Linux system, booting was taking like 70 seconds. That is a really long time for a Linux box to boot. So I knew something here was not right, because that's not a classic pattern. And I know some people don't like systemd, they like the old init system, but systemd analyze blame is really, really good for digging into and figuring out why your system is booting the way it is and what is taking time. And it's a great tool for diagnosing those boot problems. What I found, looking through our Git logs actually, was that we had a configuration error. And the system and CloudInit were recording these multiple timeouts. And we had essentially set up our images for when they were local images to not have DNS be managed by the network manager, which was great when it was local because we were coming through Vagrant and hitting our own internal DNS servers, and it was all great. But in the public cloud, it turns out we needed DNS to do our job. And so we reverted that change for these public cloud images and got better. 25 seconds boot. That's definitely better than 69 seconds. But I knew we could optimize this further, and so rolled up our sleeves some more, got in there together, looked at systemd analyze, and kept diving in to make this better and better. The next thing was DHCP. And I was looking at the logs, and it was taking like 9 seconds to get an IP. And I was no DHCP protocol expert, so I went to Google, and I was like, Wikipedia, DHCP protocol. There's like a nice little diagram of like, these are the steps DHCP takes to give you an IP. And they were not the steps I was seeing in my log. So looked a little bit more, and I noticed that the system was requesting an IP. It wasn't asking DHCP for an IP. It was like, can I have this IP? And the DHCP server was like, I'm not even talking to you. And then it would say, can I have this IP again? Like, please? And it's like, I'm not talking to you still. And finally, it gave up and said, okay, give me an IP. And when I read about the behavior, it was essentially the fact that it was trying to ask for its old IP from when the image was created, which I found bizarre because I ran virt sysprep, which very loudly stated that it was clearing out all the DHCP IPs. It turned out that there was an incompatibility between our version of virt sysprep and our version of Red Hat Linux, and so RMDash RF fixes all of the problems, and so that was the way we went down. We added that script to Packer, dropped the boot down to 15 seconds. So we're making some good progress on the optimization front here. But I wanted better than 15 seconds. So did systemd analyze again, looked more, and network manager wait online screamed out to me is still taking a fairly long time. So we looked at that, and what is that service? What is that doing? Its job is to block your system from booting. That sounds bad just to begin with, until the network is stable. And it does this for good reasons. There's lots of services out there that get very upset when they come up and there's no network, or even more upset when there's a network and it disappears on them and a new one comes up behind it. Turns out, though, SSHD doesn't care, which is great, because that's the only network service we care about when we're doing Test Kitchen. So we mask that service so that it essentially doesn't run on boot, and we bypass that whole wait for the network to come up. And when SSHD comes up and the network is there, it's well enough behaved to understand that, and that works fine for testing. I don't recommend this for like production systems, so great for test systems, but don't do that in production. So we dropped it down to 8 seconds. So we went from 69 seconds to 8 seconds. And then for the entire create process, a minute 22 down to 20 seconds. And at this pace, you're starting to get a good user experience. You're typing KCloud or Kitchen, and converges are starting. You see things on the screen. Images are booting under 20 seconds. So it's a much better experience for the user. But we weren't done. There's other steps we had to optimize. The next one was prepare, and prepare was taking a very, very long time. So a kitchen prepare, for those of you not familiar, that's where Test Kitchen, it grabs all of your cookbook files and all of your environment data and your data bags and your roles, and it sends it to the remote system for testing. And this was taking over 5.5 minutes, which was peculiar because when we ran it locally, it took like less than a second. So we had to look at the code, and thankfully it's open source, so you can figure out what's going on. And it's using essentially SCP under the covers to handle this. But in the version that we were using, it was doing it a file at a time. And our roll cookbooks have over 1,100 files in them. So each one of those round trips to a remote system was adding up to over 5 minutes of sitting there with no feedback in your console as to what's going on. So we looked around. What could we do to resolve this? And we found a couple of plugins out there for Test Kitchen that really helped us along. First one was Speedy SSH. And what this one does is it tars up those files. It tars up the cookbooks, and it tars up the node data, it tars up the roll data, SCPs it over, and then untars it. And it dropped it down to 5.6 seconds, which was pretty good. We were at 5 minutes, and now it's 5.6 seconds. It would be a little bit faster if it was a single tar, because each of those connections is still a round-trip time back and forth. And so we looked at Kitchen Sync. And this uses the rsync transport, and it seems to just do a single connection to sync everything. And it was down to 3.4 seconds. So bringing in those two elements, the optimize create and the optimize prepare, we had now gotten down to the 20-second boot and the 3.4-second prepare, and then converging could begin, which was really what we're trying to do in the first place, is converge and test our stuff. Now, on converging, we didn't optimize across 100-plus cookbooks to make them all as fast as possible. What we did was we implemented optimizations that would help all of our cookbooks in testing. And a lot of these are optimizations for remote testing, but even if you're local testing, they could still apply. The first one that we did was we utilized a tool called FPM Cookery. Is anyone here familiar with FPM Cookery by any chance? Okay. Go become familiar because it's awesome. It's a tool that lets you very easily make packages. And so what we would do is we would get all of our enterprise software that usually came with its own separate installer. It would either be a Java installer or it'd be a shell script you would run. And historically, when we started down our configuration management path, we would write all these custom resources for these code and have to deal with the fact that the custom resource has to be idempotent, and we have to deal with upgrades and all this churn just to install software. But it turns out that software installation is a pretty well-solved problem, and we didn't have to reinvent that. So we turned to this tool, FPM Cookery, which lets you easily make packages from other artifacts. And because we manage everyone's development environment, we can give them a quick command to generate all the scaffolding required to build one of these packages. And this is what this looks like. So it's a simple script that does a clean and install and then runs the actual package command inside of a Vagrant file. And we do a couple of other things in this Vagrant file. We sync over some required directories. So recipes, that's where your code goes that explains how you make a package. The staging is where your binary artifacts are stored, and we store those in source control under Git LFS for large storage. And then package is the output of the recipe. That's what we're building. In our case, it's an RPM, but if you're a Debian shop, you can build Debians or whatever you want to build. It works transparently. And then we also run a chef recipe to set up the server, to give it Git and Ruby and everything else it needs to build these packages. And then executes the script. And the recipes are really simple. So here's an example recipe. This is how we repackage a tool we use called Urban Code Deploy, the client for it. We point to the zip file to tell what the source is, and FPM Cookery will automatically go and uncompress that for us. We tell it it's a omnibus recipe, which we give it a directory, and all that means is when this thing is done, take all the content in that directory and put it into a package. We set some metadata, such as the version and revision and stuff like that. But this is the actual recipe here to do all the work to take this piece of software and turn it into an RPM. We essentially copy over a properties file, and then we run the installer.sh, and we're done. That's it. The end result is an RPM. This runs in Vagrant. So for us, we're running on Red Hat machines, so we get a RPM. If you ran it on Debian, you get a .deb at the end. It automatically uses the proper packaging tool. And that saved us a lot of time, because when you are downloading large software packages and then spinning up Java to install them or whatever method they're using, it just adds up under your test time. And a lot of these packages run across all of our systems, such as our monitoring tools. So it's important to optimize that side of it. Now, the first time in a Red Hat system when you install a package with Chef, what happens under the covers is Yum needs to make a cache. So it goes and it downloads all the repo data from all of its known repos and creates a binary database, and from there it can quickly check and see this version of the software is available, this is where I go to download it. But it takes about 15 seconds to do that. So you pay this 15-second tax on the first package you install in every single test. And I didn't want to pay that 15-second tax. So we found a way around it. We found a loophole, sort of a packaging tax loophole. We turned to something called CloudInit. So if you're familiar with OpenStack and other cloud providers, there's a tool called CloudInit that gets run whenever the node boots for the first time, and you can pass it some data that it will execute. So we write out a simple file, a simple script called yum make cache. And then we tell CloudInit to run that script using @ and to do it @now, which just means go do it immediately. And the reason we do that rather than running it directly is if we just ran yum make cache in CloudInit, all we would do was slow down our CloudInit time by 15 seconds. But @'s going to return immediately. And in the background, while the node's finishing booting, while Chef is doing the resolution of the cookbooks, while the kitchen prepare is happening, the yum cache can be made. And these are multi-processor systems, so we have CPU to spare. It's essentially a free optimization that we get. And this saved 15 seconds off of every single test, and you didn't just sit there in that first RPM package wondering what was going on. So that was a good general speed up that we had. And then data locality. So moving our testing to the cloud was great because all of our binary artifacts were also right there next to it in object storage. So when you're on your laptop, like here, if I go to install an RPM, I have to download it from somewhere. And some of our RPMs are over a gigabyte in size. And so that can take a lot of time to pull that down and before you can even install the package. But when it's right there, you got these quick wins for all of our packages. Like converges were just happening like that for all of our package installations. The last phase that we spent some time optimizing was the setup of the verification. So the verify phase for Test Kitchen installs a couple of gems, and then it can execute your test plan. So we essentially did the same trick with @ in which we wrote out a script to pre-install the stuff needed for the verification, and then ran it @now, and we saved another 5 seconds. So it was a small optimization, but still 50% of the time was saved by doing that. So overall reduction, we started at 7.5 minutes of non-converge time to prepare to converge, down to less than 30 seconds. And it gave us a really good overall user experience. But it was really only half of the benefit of the cloud-based testing. The other part was that it is awesome for concurrent testing. We have recipes and cookbooks that can have 7 or 8 test suites across 2 different operating systems. So that's 16 tests you have to run, 16 VMs you need to spin up. And some of them were large. So we had tests that would take 4 hours to push out to test across all those platforms locally. But the benefit of doing it remotely is that we can do that in parallel or concurrently for free. There's no slowdown when you're doing 16 versus 1. If you tried to do 16 on your laptop, it would crush it. Like, you couldn't do it. But we could take things that were now taking 4 hours, we're taking minutes just by doing them in parallel and doing them out on remote resources. So we had to write a couple of tools to support this testing. The first one was that we built a kill switch into our test servers using CloudInit again. You know, you test locally and you forget to destroy your instance. It's not a big deal because you remember at some point in time. But if you do it in the cloud, you're now blocking a resource for someone on your team. So the kill switch is set to run 30 minutes after the node is created. It just uses an @, again, and it makes sure the Python client's there, and it kills the node from within itself. And that was great, except for people were like, hey, I was working on this node, and it went away on me, and that wasn't really cool. For some reason, I don't know why that bothered them, but it did. So we added a reset into this. So any sort of login into the test system, whether it's Test Kitchen doing a Converge or a Verify or you logging in yourself to look at something, killed that old @, started a new one, and reset the timer. And that works very well for us. This is some tooling that I wrote to help find hotspots for optimization. It works both remotely and locally, depending on what you're doing. I'd hoped to open source this for today. I could have it all ready, but I'm still waiting for the legal approval. So as soon as I get that, I will fully open source it so you guys can grab it if you want to optimize your local or your remote test runs. And it gives you 3 analyzing tools built into it. The first one lets you analyze the create, and it splits between the boot and the image launch. The second one gives you recipe timing, so you can just run it and see which recipes take the longest across one or more of your test runs. And then the last one is the duration of individual steps, so it just takes all your steps and times them and tells you which ones take the longest. And if you have it across some role cookbooks, you can sort of dive in and say, I can spend some time here and get a good optimization for all of my tests. And this was very helpful because we had one package we had that was not built with FBM cookery. It was actually like a handcrafted, artisanally made package that we had. And the default for that package was LZMA2 compression, which was great because it made it really small. But it was also a gigabyte-sized package. And so it took 1.5 minutes to uncompress it and install it. And we changed that to gzip, and it went up by 15% in size, but installs in 17 seconds. So that data locality I could talk about sort of got rid of any sort of benefit of smaller compression. All right, so I have a lot more details on my blog about the individual steps and optimizations, about how we optimize various phases. And I'm also on Twitter if you have questions.
Did you guys like that? It was good? It was helpful? Applause?